What's coming off around here?
If you guys playing railroad anymore today, there's a landslide, a new cut.
Welcome back to Fun with HO Scale Stuff. This is episode 13, and it will be part 3 of DCC Under the Hood. In parts 1 and 2, I discussed, well, in part 1, first I introduced the fact that the DCC signal is an AC square wave. And in part 2, I presented some various forms of approximated circuitry to just give viewers an idea of about how the signal could be managed from both creation and as well as its decoding by the decoder. So that covered, we also recall that in that discussion, I explained that the pulse widths of the square wave are actually the codes of ones and zeros that constitute the DCC control packets that are being transmitted from the throttle out to an addressed locomotive. So in this part 3 of DCC Under the Hood, I want to explain more about what the designers did with those ones and zeros in order to create the complex code that we enjoy using to control our locomotives on the train sets. So if you will, allow me to continue with that process of explaining it and introducing some of the greater parts of what that whole complex system is. I'll try to make it very simple for you and break it down into actual component parts. If this becomes to you somewhat interesting, I'd like to ask you to please leave a like. And also, if the channel seems a bit interesting to you, why not subscribe? I'd really appreciate that. And hang around for a while to see if there isn't more things happening here that also are enjoyable for you. So with no further ado, I'll continue with my presentation on DCC Under the Hood, Part 3. So previously, in our discussions about the DCC signal, it was pointed out that the AC square wave content is comprised of durations, so that the signal code is actually comprised by those various durations, and I characterize those as ones and zeros for the sake of bits, that either it's true or false or however you'd like to look at it, but I think it comprises certain bits. And the discussion here is about these bits and that they comprise a packet, and the packet is going to be defined for you shortly, but it's the means by which the controller is continuously transmitting commands to the track in an organized way. So to begin with, understand that what we said was, recall it's a AC square wave, and that, as I'd said, it has long and short pulses, and these are defined as a 0 and a 1, where the 0 pulse width, remember we're talking about durations here, so this duration here is going to be somewhere between, it's going to be around 100 microseconds. The spec allows for plus or minus 3 microseconds. And the 1, this duration here is going to be around 58 microseconds. And this stream of bits, which we're calling now, we're going to call them zeros and ones. So these zeros and ones are being transmitted by the controller to the track. So we have the track and it's getting all these zeros and ones, and the decoder is going to read these zeros and ones as we kind of demonstrated with our approximated circuitry, and it's going to organize them into the commands that they contain through the manner in which the bit stream is organized. So the organization breaks down into 5 parts. There are 5 basic parts to how the protocol is organized. So we look at the protocol as 5 parts, starting with there's a thing called a preamble. And we'll talk more about it, but just know that the very first sequence of bits that it sees on the track is this preamble, okay? So once it sees a preamble, it's going to see a thing called a start. And as I say, more of that, but this preamble is actually is a pattern. It's a pattern of bits of these ones and zeros. It's a specific pattern that's recognized by the decoder, but it's only recognized when it sees a start, and that's a single bit, and that bit is different from this pattern of preamble bits, and that's how the decoder knows, oh, something just occurred, I think I see a start, and it can check to see if the start was in fact a valid preamble. The third thing we're going to see as part of the protocol is the address. And then the address it's a collection of bits of either 8 or 16 bits that identifies a unique address. So the decoder is going to look at that address value of the next subsequent number of bits and say, is that me? Then the next thing we're going to see in the protocol is the command. So the command is, again, an organized set of bits with a distinct pattern that identifies a unique DCC command. That's hard to read, but it says command. But I'm just saying that it's just going to be, again, 8 or 16 bits of command data. And if the address was, in fact, this decoder's address, it's going to then also decode that command to a specific command, and it will execute it. Only in the provision, it will execute the command in the provision that the next part of the protocol is satisfied, and this is called a checksum. And this is an 8-bit value that is a checksum of the previous 2 components, these 2 components here. So this checksum will either be correct or incorrect, but if it's correct, then the decoder, if it was addressed, will execute that command. So, well, before I go into more detail about the individual parts of the protocol, I want to add one more thing, is that at the end of the protocol is a single event called I guess it's called the end, which makes most sense. It's the opposite of a start, and the end is just a single bit, and it is a special level that must be there for all of the protocol packet and the entire protocol message to be able to be decoded correctly. If the end bit's not the correct value, then the decoder is going to throw the whole thing away. And there is a bit of discussion about because of gaps in the rail and because of noise, potential noise on the track, it's quite likely that the decoder is going to drop packets. And the specification from the NMRA is to be sure that whatever the throttle or controlling device is for creating the DCC that it repeats itself frequently, so that in the event, for instance, that a message was sent to a decoder to say stop, it would be appropriate to send that message over and over again, so that in the case that the decoder did reject the one or two of those stop packets, it will still get one. So before I go too far into the discussion of the DCC packets and their individual parts, I want to jump out, kind of get back up onto a higher level and discuss the DCC overall architecture that the DCC designers had in mind. So we have to have a power supply, that's a given, and then there's some control, which is the user interface. And this control allows the user to create the specific DCC commands that are going to be transmitted to the track. The DCC output from the control, as we talked about, is a signal. It's a signal that is a AC square wave signal. And this signal is presented to various decoders that are potentially on this track. The point of DCC, which is nice, which is much nicer, I should say, than the DC control, is that you can have multiple locomotives or accessories getting their instructions from a single controller all on the same track. So in this instance, what I've shown here are the two kinds. I've actually shown two kinds of decoders: a multifunction decoder and an accessory decoder. And to what I just said about having multiples, you can have more than one multifunction decoder or accessory decoder, provided they have different addresses. So this is address 3, and this other locomotive is at address 4, and that's quite all right because the controller can address uniquely either one of them. Now with accessories, their address space overlaps the multifunction decoders, and when I discuss addresses as part of the packet discussion, I'll explain why that is. But accessories also have individual addresses. But what these decoders have in common is that they must have up front some analog circuitry that produces a DC voltage, and this is very hard to see, but that says DC voltage. So it's going to produce a DC voltage to power up this microcontroller that's part of the decoder. And it's also going to produce the pulses. Now, we discussed that previously about how circuits might be used to produce these two signals in this analog portion. Now, this part of the decoder is going to have outputs, and it's going to have analog and digital outputs. And the analog output will be producing voltages and current to control the motor, both its direction and its speed. And the digital outputs produce outputs on and off that control lighting, for instance. So where all of this architecture gains a significant amount of complexity is that it's possible to program decoders so that you have the ability to configure each decoder for various reasons. And the manner in which that's done inside of each one of the decoders is a series. Let's just do it like that. Is a series of basic registers. If you're familiar with microprocessors or microcontrollers at all, you know that they contain programmable cells of registers. And these registers, in the case of DCC, they're called CVs. And what that stands for is control variables. So control variables have many of them are predefined by the NMRA, which is the National Model Railroad Association. And NMRA, for example, the very first one, location 1 of the CVs, is the decoder's address. The address of the decoder, for instance, this 3 for that multifunction decoder would be in this CV number 1. So this scheme, if you will, is the overarching architecture of DCC control. So I'll continue now with my discussion of the packet. This image that you see is the scope trace of a valid DCC command. It is the AC square wave that was recorded off of the track. This captured it's a DCC command that was sent to address 3, and it was a command that directed the decoder to turn on the light. As you see here, that the leading portion of the packet bits is the preamble circled in red. Preamble consists of a sequence of just 1 bit, and the 1 bits that are required according to the NMRA standard for a command station is 14 ones, which if you count these 1 bits, there's 14 of them. Recall the 1 bits, as we'd mentioned earlier, are the short durations, and the zeros are the long durations. So you can see where the cluster of 1 bits are. There are 14 of them. And it also, according to the specification by NMRA, that the decoder itself is required to decode a preamble after receiving 12 consecutive 1 bits. Well, as you can see in the next image, the preamble 1 bits are terminated by a single 0, which is the start bit for the packet information. The very next bit of information following the start bit of the packet is the packet's address. That is the address of the intended decoder device to receive the instructions that follow. This particular address is a short address to location 3. What makes it a short address is the leading bit, circled in orange, is a 0. Whenever an address has a leading address bit 0, the subsequent 7 bits are the entire address. A short address is one of 6 types of addressing that have been defined by the NMRA specification. The table that I'm showing here is a table I created from the DCC specifications. It shows the address formats and their particular ranges that are capable with each type of address. And you see the second one from the top starts with a 0, and then it has 7 little a's, which indicate those are the address bits. And it gives you anything from address 1 to 127, and it's a multi-function address. So the other types of addressing here you see is an address that begins with a 10. And there are 2 of those. There's the 3rd and 4th from the top, and each one of those accessories can have its own address range. So you can see from the table that it's possible to have an address 1 for the multifunction decoder, which is the short address, the 7-bit loco short, and then have the same address 1 for an accessory because of the difference in the first 2 bits. So the first 2 bits then pretty much define what the address type is going to be. I should also point out that every group of 8 bits that are part of the packet data, regardless of its purpose, is separated from every other group of 8 bits by this 0 bit that I'm showing here, circled in red. Just for clarity, I want to point out that the address may require an additional 8 bits. It would just depend on the address type. And of course, every 8-bit group has a 0-bit separator. What follows that address is the instruction data that is comprised of as many as 3 8-bit groups. In this instance, however, it's just 8 bits. It's a simple instruction, and it's circled in red as I show here. What you see here is a table that I created. It's a set of all the DCC commands that I created from the NMRA DCC specifications that you can find online. Let me scroll down through this table. Hopefully this will impress on you just how much complexity exists within the DCC specifications command capabilities. You can see that the command bits in the scope trace presented has a binary signature of 10010000. So using that command pattern, it's possible to show this exact command in the command table. The command corresponds to a multifunction decoder command because of its address's initial bit, which is 0. Next, the command pattern's first 3 bits are 100. So searching the local short portion of the table finds that this command is a function group 1 command. In the function group 1 command, you see that it shows D, and that just identifies the data field for that command. But the initial D after the 100 is underneath it shows that it's a C, meaning it has a special meaning, and then there's N following that, which means that each individual bit has some functional meaning as well. But the C was unique, and that happens to be bit 4. Starting from the right to the left, if you're looking at the D's, for instance, the first one on the right is bit 0, and then as you go to the left, it's 1, 2, 3, and 4. So if you look at the description of the function group 1, it says bit 0 through 3 set F1 through F4, and those are function bits that are, from a controller perspective, like on your and if you have a cab controller, for instance, or whatever type of interface you're using to control your DCC, function bits are kind of a shortcut command that instructs the locomotive to do some simple thing. And in this case, the function bit 0 is actually sometimes called FL. If you look at the bottom of the description for function group 1, it has FL/F0. And if it's a 1, it's on, and if it's 0, it's off. And that's true of all 4 bits. But I'm drawing your attention to the F0 bit because that's the one that's set in the AC square wave signal that we were looking at in the command. And so that bit is instructing the decoder to turn on the headlight, as that's what's the definition of an FL, as function light. So what we've covered through this discussion of the DCC packet has been these 4 parts of the packet: the preamble, the start bit, the address, and the command. The yellow circled areas, those are the spacers that, as I mentioned, there's a 0 space that's placed between every 8-bit grouping. The next thing that has to be discussed is the final part of the packet, which is the checksum. And the checksum involves some amount of understanding of binary arithmetic. As in the world of binary, it can be a little confusing if you're not familiar with it. So let me just take a moment to introduce the final part of the packet, which is the checksum, and explain how an XOR, or exclusive OR operation, as well as binary values, actually work. Binaries arithmetic, some of you probably already know all about binary, but just for those who don't, binary is a 1 or a 0. That's the limit of the numbers that exist in the binary world. So in that there are various operations that can be logically performed with ones and zeros. One of the things that we should first discuss is we said that the address of the multifunction decoder in the waveform that I showed was 7 bits and looked like this. Well, I said that that's address 3. Well, in binary, just like in decimal numbers, if we were looking at it from a decimal world, we would say that that is 11. But in binary, that's 3. And the reason why is let's begin with in decimal world. In the decimal world, this is a 1, or what they call ones. It's either 1 through 9, or 0, actually. It's 0, pardon me. It's 0 through 9, but then starting in this position, it's 10 through 19. So if you had 1, 1, it would be 1, 10, and 1, 1s. 10 plus 1 is 11. So that would be then called 11 in decimal. But in binary, the positions aren't by 10, they're by 2. So in this position, the value can be either a 0 or a 1. In this position, you'll see in a second, but in this position, then this would be either a 0 or a 2. And then in this position would be a 0 or a 4. So, and it goes on in multiples of 2 like that. So you start with 1, 2, 4, 8, 16, and like that. They just keep on multiplying. Just the same as it is in the decimal world. You don't think about it much, but when we were taught originally how to deal with numbers in elementary school, these positional things, it was called positional notation. And so they would be like 1, 10, 100, 1,000. And the same thing happens in the binary world. So in the binary world, we got 1, 2, and 1, 1. So that's 3. 2 plus 1 is 3. So we get an address of 3. I hope I did that well for you. This can be a confusing subject if you've never dealt with binaries. Let me move on. The next thing I want to talk about is what we call an XOR, or exclusive OR operation. And it's typically drawn with a logic operator. It looks like this. And you have 2 inputs, and we're going to do some arithmetic operation on them. And, depending on what these 2 bits are, determines what the output is. And in so applying any combination of bits, if we create a small table and we say these are the possibilities, we know we have 0, 2 zeros, or we have a 0, 1, or we have, nice, we have a 1, 0, or we have a 1 and a 1. So those are our 4 combinations for inputs to our XOR gate. So it's XOR arithmetic. And what would be the consequence of each of these combinations under an XOR operation is a 0 and a 0 is not exclusively ORed, so it's 0. A 0 and a 1 is, exclusive OR. It's this. And then here we have a 1 and a 0, and again, that's exclusive, so we say that's 1. But here we have 2 1s. They're the same, so they're not exclusive, so we put a 0. So that's the XOR function. When we talk about the actual signal that we had, we recall that we had 2 components that we incorporate into the final XOR or checksum value. And we had an address and we had data, or a command actually is what we really had, was just like that. And so the address and command data, when you perform a bitwise XOR, for instance, we had 0, 0, 0, 0, 1, 1, 7 bits, and that began with a 0. That was our actual address. And so the data 1, 0, 0, 1, 0, 0, 0. So we have these two values in our AC square wave signal. And when you do the exclusive OR on this, you look at each bit position and perform it bitwise. So 1 and 0, that's exclusive. 1 and 0, that's exclusive. 2 zeros are not, yes, no, no, yes. So we would expect then that the final checksum for this packet should be 10010011. So let's go back and look at the packet and see if that's what happened. Sure enough, when you see the results of the packet here, it shows 10010011, just as we computed with the XOR. So that would be a valid packet, except for one additional detail, and that is where you see the green circle at the end of the checksum, that value has to be a 1. That is the end bit. So that covers the entire range of the DCC packet, at least covering the major parts. And I hope that gives you a fundamental understanding of the DCC protocol. So I found it very interesting, and I hope you did too. And I want to thank you for watching this video and for any feedback that you might be able to offer me or questions. Do appreciate your comments. And if you would also be so kind as to, if you found it entertaining, please leave a like. Thank you very much.